Imagine this. A satellite worth billions of dollars is tumbling through the void a million miles away. Something's gone wrong, and its camera can't point where it's supposed to. You can't exactly send out a repair crew, right? So the fix has to happen from a control room on Earth, and it has to happen fast. Well, today, we're diving into some really cool research that's found a brand new, much smarter way to figure out exactly what's broken. Okay, so here's how we're going to break this down. First, we'll get into the amazing tech that keeps these satellites pointing the right way. Then, we'll look at what happens when things go sideways and how engineers have tried to deal with it in the past. After that, we'll get into the meat of this new, smarter diagnostics, see how it actually performed in tests, and wrap up with why this is such a game-changer for space missions.
All right, first things first, let's talk about the incredible gyroscopes that are basically the secret sauce to a satellite's sense of balance.
At the center of all this is a device called a control moment gyro, or CMG for short. You know how an ice skater can spin faster or slower just by moving their arms? Well, a CMG is kind of like that, but on a massive, super high-tech scale. By tilting these incredibly fast spinning flywheels, a satellite can generate huge forces to adjust its position, what engineers call its attitude, with unbelievable precision.
And that precision, it is absolutely everything. We're talking about keeping a communications satellite perfectly aimed at a tiny spot on Earth, or pointing the Hubble telescope at a galaxy billions of light years away without wavering. They're what allows satellites to perform complex moves in orbit. Simply put, if the CMGs fail, the mission fails.
And that gets us right to the heart of the problem. As the research points out, these gyros are tough, but they're not invincible. They can and do malfunction. So how on earth do you figure out what's wrong with a tiny part in a complex machine that's floating in the vacuum of space?
Right, so let's take a look at how engineers have been wrestling with this exact challenge for years.
You see, the really tricky part isn't just getting an alarm that says, "Hey, something's wrong." That's not enough. Mission control needs to know which gyro is acting up, what is wrong with it, and how bad the problem is. And they need all that information like right now. And this has been an ongoing effort. The first big attempt, the CAUKF algorithm, was kind of a brute force method. It had to check a massive number of possibilities, which made it pretty slow. Then came an update, GOUKF, which was smarter and narrowed the search. And now we have the subject of this research, the SGAUKF, which takes a much more streamlined and frankly more elegant approach to the problem.
So now for the big reveal. What is this new algorithm doing that's so much smarter?
The big idea is actually a very clever shortcut. Instead of just throwing computing power at the problem and checking every single thing that could possibly be wrong, the SGOKF leverages the physics of the system itself.
And this slide really lays out the genius of it. The old way was like trying to find a burnt-out light bulb by unscrewing every single one in the house. The new method is way smarter. It knows all the gyros are connected and influence each other. So it's like flicking just a few key light switches. Based on how the rest of the lights flicker, you can instantly tell where the problem is. By just checking the odd or even numbered gyros, the system's reaction tells you everything you need to know about the others. It's brilliant. And the payoff for that clever logic is just a massive boost in efficiency. You don't have to be a math genius to see what's happening here. For a typical satellite with 4 gyros, the old method had to crunch through 16 different scenarios. This new method, it only has to check 4. That's not a small improvement. It's a fundamental change in how much work the computer has to do.
But of course, a great idea on paper is one thing. In engineering, you have to prove it works. So the researcher put this new algorithm through its paces with a whole bunch of simulations to see how it stacked up against the old methods.
And the results are pretty amazing. Just look at this table. It shows how accurately each method could pinpoint the fault. Whether there was a little bit of signal noise or a lot of it, the new SGAUKF method, that's the last column there, was the winner every single time. It averaged over 94% accuracy, which is the best of the bunch.
But here's where it gets really exciting. It's not just more accurate, it's also a whole lot faster. This chart shows how long it took each algorithm to actually do the diagnosis. And you can see it right there. The new SGAUKF algorithm got the job done in just over 6 seconds. That's way faster than the nearly 9 seconds it took the next best method.
Let's just put a big number on that. We're talking about a nearly 27% drop in the time it takes to diagnose the problem. When you're in a crisis situation and a billion-dollar mission is on the line, saving those few seconds is absolutely critical. It can be the difference between saving the satellite and losing it forever.
So let's just zoom out for a second and think about the big picture here.
What does having a faster, more accurate diagnostic tool really mean for space exploration? Well, it means our satellites get tougher and more resilient. They can figure out what's wrong with themselves and adapt to problems way faster. That makes the whole mission more reliable, it lowers the long-term costs, and, most importantly, it dramatically increases the odds that the mission will be a success.
And the author of the paper, Option Rahimi, really sums it up perfectly. He calls this a promising option for diagnosing these complicated systems. Why? Because it delivers top-tier accuracy while needing way less computer power to do it. That's basically the holy grail for this kind of engineering.
And this kind of leaves us with one final exciting thought. Every time we make an improvement like this, no matter how technical it seems, we're pushing the envelope of what's possible. When we can build spacecraft that are more reliable and more autonomous, we open up the door for even more ambitious missions, to go further out into our solar system and to see deeper into the universe. So the real question is, with smarter tech like this, what new frontiers will we reach next?